Okay, so now we want to show this axiom of extensionality. And this is probably, in a way, the hardest one because it involves for all and exponential objects, but it's not that bad. So the axiom of extensionality then. For all little a of type A, we have that evaluating. So here, little f and little g are variables of type b to the power of a, and the claim is that for all a, we have evaluating f on a equals evaluating g on a, and all that implies f equals g. So basically, this is saying that if f and g agree on all inputs, then they're the same arrows. Okay. How do we prove it? Well, the idea is basically going to be to look, and by the way, we could also put a implication arrow going the other way around, because this obviously holds when f equals g as well. But anyway, let's not worry about that. The main thing is to show that the left-hand side always implies the right-hand side. So what we're going to do is we're going to suppose we have a general arrow h comma k into b to the power of a times b to the power of a, and we want to show that if h comma k is in this extension of the thing on the left, then it's in the extension of the thing on the right. Okay, so firstly, how are we to understand this extension of the thing on the left? So this is, in other words, the extension of for all a, f evaluated on a equals g evaluated on a extended over f and g in b to the power of a. Well, we can just say that that's the subobject classified by the interpretation of for all a, f evaluated on a equals g evaluated on a. And then we can, so we're interpreting over f and g and finding the subobject classified by that. And then we can just like work out what this interpretation is. So it's going to be for all subscript a transpose of the interpretation of evaluation of f on a equals valuation of g on a. That's interpreted over f, g, and a, and then we can transpose it, and then we do that before this for all a arrow, and then we find a subobject classified by that. Now, if we just call r the extension of evaluation of f on a equals valuation of g on a over f, g, and a, then this thing here is clearly going to be the transpose of the classifying arrow of r. So we could call it chi r transpose, and we can write this whole line then as the subobject classified by for all a after chi r transpose. And we have a name for that. We can call that for all little ar. That's the universal quantification thing that we've already encountered. And by theorem 13.9, so you can see the video universal quantification proof for a proof of that theorem. Anyway, by that theorem then, we're then going to have that h comma k is in for all ar. Oh, by the way, notice what I'm doing here. I'm writing this object here that this is a sub-object of as b to the power of a times b to the power of a in brackets times a. So that turns out to be useful. Anyway, by theorem 13.9, as you can see in this universal quantification proof video, we're going to have that h comma k is going to be in this big extension here, as in it's going to be in this, if and only if h comma k times the identity arrow is in R, where, as again I say, R is the extension of f evaluated on A equals g evaluated on A over f, g, and A. But here we want to actually work out what R is. So R is the subobject classified by, like, working out the interpretation and so on. It's the subobject classified by delta B of the productive pair of the interpretation of E FA over FGNA and EGA over FGNA. but we want to represent things. So, I mean, here we have these interpretations over arrows F, G, and A. So normally we would just say, oh, you know, F becomes P1, G becomes P2, A becomes P3, and so on. And that would be doing this kind of thinking if we weren't having the brackets there, but we do have the brackets there. So in order to get our EF, in order to get the FA to do the E on it, when we're interpreting, we can think, well, I just do the product of P1 times identity of A, and that obviously selects the first BA and the A, and then we do the evaluation after that. So this is because of the way we're thinking of the kind of source objects that we're interpreting over. And alternatively, we could, you know, think we'd do an isomorphism and then we do P1 and P3, but this turns out to make the maths a lot easier to do it this way. So the interpretation of EFA over FG and A, we consider that to be E of P1 times 1A, because the P1 is selecting the F from here, and we times by 1A because we're keeping this on its own over here, okay? And in a similar way, the interpretation of G, comma A over FG and A is just going to be, sorry, in a similar way, the interpretation of E after G, comma A over FG and A is just going to be E after P2 times 1A. And so this R here is just going to be the sub-object classified by delta B, E P1 times A, comma E P2 times 1A. And this is, of course, just going to be the equalizer of E P1 times 1A and E of P2 times 1A. And so basically, we've got that H comma K is in our original extension, that is the extension of for all A, F evaluated and A equals G evaluated on A. By the way, yeah, the way I got these things here, by the way, is just interpreting this, okay? So this is basically just a sort of expanded out version of what I could write as the interpretation of F A equals G evaluated on A over F, comma G, comma A, sub-object classified by that. Anyway, and it works out to this. But the point is that H and K is in the big extension if and only if H, comma K times identity is in R. And then since we've just shown that R here is just the equalizer of this and this, we're going to have that H comma K is in our original extension if and only if doing E P1 times identity after H comma K times identity equals what we get when we do E P2 times identity after H comma K times identity. And so then we just have to work out what they are. So, you know, replacing these products with, actually, I think it's easy. Yeah, there's probably a direct route, actually. We just compose components and we see immediately that this is just going to be H times identity. This is just going to be E after H times identity. And this is immediately going to be E after K times identity. And so H comma K is going to belong to our original extension if and only if these two things are equal. Okay. Anyway, I took some effort in expanding those out. You can see you're working here. Pause the video if you want to work through it, but there's no point because there was a shortcut. Anyway, so basically, we're going to have the h comma k is in our original extension if and only if e after h times identity equals e after k times identity. But notice that this is just really the kind of I like to call it the anti-transpose, but you know what I'm saying is that if we wrote that h is equal to h dash transpose, then, well, okay, let's say it a different way. If I wrote that h here, no, that's okay. If I wrote h is equal to h dash transpose, then this expression here would just be h dash. Okay, so in that way, I kind of call this thing, and in a similar way, so for that reason, I kind of call this e after h times 1a, I call it the kind of anti-transpose of h, okay, because it has the property that like if we get the anti-transpose of h and then we transpose it, we get h, okay. And in a similar way, this could be considered the kind of anti-transpose of k. Like usually authors will just say, well, it's just a transpose, so I'll have this special terminology for anti-transpose. I think of the one that makes an arrow that actually goes into an exponential object as the kind of transposed arrow, but we're not actually putting notation on this. And then the other one, and so if you can get such an arrow that goes into an exponential object and then you undo it using the exponential arrow correspondence, I call that the anti-transpose. But most authors don't usually distinguish, they just call either one of them the transpose of the other. So they'd say something like, for example, in our case here, we have that this goes from h to b to the power of a, does our little h here. And then the other one, the kind of corresponding one, I call it the anti-transpose. And that obviously goes from h times a to b. I call that h anti-transpose. But, you know, most authors would just say this is also the transpose of this, just as this is the transpose of this. And that latter point I would agree with. But anyway, doesn't really matter. The point is that we have h antitranspose equals k antitranspose, which implies that h equals k, which implies that h comma k belongs to the extension of f equals g along over f and g, and that's it, because we've shown star, we're seeing stars, because star is here is what we wanted to show. So we've shown that if we have an arrow hk in the extension of for all a, f evaluated on a equals g evaluated on a, then we have our general arrow hk's in the extension of f equals g over f and g. Therefore, this subobject is contained in this subobject. Therefore, this formula here implies this formula here. And that's the axiom of extensionality.